Hi everyone, and welcome to the exercise on many objectives and disciplines. Here is the table of contents of the exercises. So we passed the two chapters on optimization algorithms, and we can start right away with the first exercise here. It is on Pareto optimization. So at the bottom you see a steering system. So the steering system consists of a steering wheel where the driver gives the input to the wheels at the end of the tie rod, and how it works is that the movement goes from the steering wheel through the steering column. Then there is a steering gear, which is transferring the motion from a rotational movement to a translational movement on the rack, and the final movement, as I said, ends up at the wheel with the tie rod. And one key ingredient in modern steering systems is the EPS actuator. So this is a motor which is supporting the steering maneuver. And what is our engineering problem? So what we want to do is we want to find the optimum actuator power, P EPS, and steering gear ratio, ISG. So those are the design variables for the steering system with respect to two quantities of interest, which are the steering wheel angular speed, omega, and a minimum steering wheel angle at the end stop, which is phi. The steering wheel torque applied by the driver is set to 10 Newton meters. On the next slide, we have some data which is needed to solve the task. So don't be afraid of so much information, but it's rather simple to solve it afterwards. So what we have are just some given values as the rack end stop. So this is the upper bound for the rack movement. We have a resistance on the rack itself. So here on the right side we have another sketch on how the steering system works. So we have a resistance on the rack. So this is working against the movement of the driver. So this is due to resistance of the wheel on the ground and so on. We also have a steering wheel torque, which was also mentioned before. So this is the 10 Newton meters as an input. We have upper and lower bounds for the steering gear ratio. So it's supposed to be between 70 and 100 rad divided by meters. Here are some formulas as well. So how is the steering gear ratio calculated? It's calculated out of the angle of the steering wheel divided by the rack movement. So it's a classical formula. And the power of the EPS actuators, or second design variable, is supposed to be between 0 and 600 watt. And there is another formula. So the power of the EPS actuator has to be higher than the velocity of the rack multiplied with the steering assist force on the rack. And we for solving those equations, we assume a quasi-steady state. So here's just an equilibrium of the forces consisting of the force of the EPS activator. Then we have the input force due to the input movement of the driver, and we have the resistance force, and this should be in the equilibrium. Once again, I want to press that formulas like that in the exams are given, so don't be afraid. You don't need to be some expert or some automotive engineer. We have two tasks. The first one is, which I kind of also mentioned before, is identify the quantities of interest and set up the corresponding objective functions and state the optimization problem. And the second one is that we want to calculate the Pareto front by displaying one quantity of interest as a function of the other one. So we want to do it similarly as in the lecture. Alright, let's get started with the first exercise. So as stated before, we have two quantities of interest. We have the maximum steering wheel angular speed and maximum, actually answers it. So what we need here? What we need here for the first quantity of interest is a minus sign, since we always want to minimize. So we take this velocity as omega, steering wheel max, and the second quantity of interest is the minimum steering wheel angle at the end stop. So this is y2. Here we don't need a minus sign, so we just take the angle of the steering wheel at the end stop. And now we also formulate the objective functions. So the first objective function with respect to the speed is f1, and here we can just use the formula. So how can we calculate the angular speed? So the angular speed can be calculated by the gear ratio and the rack velocity. The rack velocity can be seen here. Wait just 1 second. So this is the rack velocity, and we can calculate our angular speed out of the gear ratio. So it's basically the same as for the translation and the rotation. And if we do that, then we say our objective function with respect to the angular speed is minus omega steering wheel max, and we can reformulate it with the mentioned formula. So we take the minus of the gear ratio here multiplied with the rack velocity V max, and then we can also use the formula for the velocity further, which is okay, something's not working properly. Anyway, so this works now, and we can calculate the velocity out of the power of our EPS actuator divided by the force of the actuator. So it's just the power EPS divided by the force EPS. And with some additional math, so we can now also enter the formula shown at the right side for the equilibrium. So here we just entered this formula within the resistance force as well, and the motor steering wheel moment, and then we can enter those values as well and end up with this formula. So it's minus the power of the EPS actuator divided by the resistance force divided by the ratio of the gear minus the torque of the steering wheel. So this is our first objective function, and the second objective function is a bit easier because this is only related to the minimum steering wheel at the end stop. So we can use the formula given on 2 pages before at the end stop, which is equivalent to the translational movement of the rack. So it's R end, multiplied with the gear ratio as well. And then we have our two objective functions, and the last thing is also we can use the compact notation to show how it's working. So we have one design variable, which is the power of the actuator here. Our second design variable is the ratio of the steering wheel gear, and then so these are our design variables. And from the formula we can see that with respect to the first objective, both design variables are influencing the velocity, so the steering wheel velocity, the angular speed. So here we have our minus omega steering wheel max, and this is influenced by both, whereas the minimum steering wheel angle at the end stop is only influenced by the gear ratio. So therefore the second quantity of interest is only influenced by one design variable here. Now the last thing we need to do is, so here it's also written in better fonts for you, and we can now also set up the objective function, or the objective function, the design space for lower and upper bounds on the design variables. So we just set up the classical optimization problem, which is we want to minimize with respect to the negative of the velocity. So we can also just take the y1, and with respect to the minimum steering wheel angle y2. And so far we haven't decided how to deal with those two quantities of interest or those two objectives, so we just put it in brackets, and we can also write down here what the design variables are. So it's the gear ratio and the mentioned power of the actuator. And subject 2, what we have so far only upper and lower bounds on both design variables. So we have a lower bound on the gear ratio, which are this dimensioned 17 rad per meter. Just a second. So I will remove this quickly. Not so quickly because it's not working for whatever reason. Doesn't matter. So we put a meter out of this one. Oh, perfect. And the upper bound of the gear ratio is now 100. And the same thing for the second design variable. So this is the power of the actuator, which is also a lower bound. So it has to be equal or greater than 0. And the upper bound is 600 watt. And with this, we have now set up the optimization problem for two objectives and two design variables. Next, we will deal with the Pareto front. During this exercise, we will follow two different approaches. The first one is more graphically based, and the second one is more mathematically based. We will start with the graphical approach, which is of course not possible in, let's say, a high number of dimensions, but with this simple example we can do it. And how this works is that we first look at the formula we have. So we have the formula for the first quantity of interest, which is the maximum steering wheel angular speed, which is affected by both design variables, so by the power of the PS actuator and the gear ratio. And then we have the second quantity of interest, and this is important, which is only affected by one design variable, which is the gear ratio. And in general, we can say that since we want to minimize both, so we want to minimize y2 and y1, the designs want to go in the left lower corner, because here, according to the axis, are the values with the lowest y1 and y2, so this is beneficial with respect to our optimization problem. So what happens to our objectives when we change the design variables? So for the performance power, so the power of the EPS actuator, it's quite easy because it's not affecting y2. So what we do is the higher, so for a given gear ratio, the higher the power of the actuator, the lower is y1. So this is pretty easy. So this is how the quantity of interest do change. So no change in y2 when we change the power. For the gear ratio, it's a bit more complicated. So if we increase the gear ratio, we also increase the minimum steering wheel angle at the end stop. For the gear ratio with respect to y1, it's a bit more complicated, but in the end, if we increase the gear ratio, we first decrease this whole term, but we have this minus sign here, so that's why we decrease y1. So that means if we're increasing the gear ratio, what happens is we increase y2 and we also decrease y1, so that's why we change our quantities of interest in this way. And now let's think about where the Pareto front is. So we know that for each design we have, so if we choose one gear ratio, we always want to have the highest power of the actuator. So that means for a specific design, let's say we are here, we come to the upper bound of our power of the actuator, and then we are done. The only thing that we can do is we can now change the ratio, and then we will end up at a different design where the y1 is decreased but y2 is increased. So we could, let's say, if we change the design, so we change the ratio from here, we would go here and we'll end up again at the upper bound of the performance value, but for a different gear ratio. So that means that our Pareto front will look like that. So it's a straight line, a straight decreasing line. So out of this we can conclude that our Pareto front consists of all designs with different gear ratios and the power of the actuator at the upper bound. And all of this within the design space of the gear ratio. So that means the gear ratio is supposed to be between 70 and 100. As I said in the beginning, we can do it in two ways. So the second way is the mathematical way. So here we need to prove. So we are not doing it with any graphical interpretation, but we prove that those this Pareto front, which we derived graphically, is indeed the whole Pareto front. And there we have two steps. So remember that the Pareto front are the designs that are non-dominated. We had that in the lecture. So that means that there is no design that has better values for all quantities of interests. And the first step is, so step one is to show that indeed all designs within our specification here are non-dominated. So we are saying that all designs within the bounds of the design space are non-dominated. So with this we prove that our derived designs are at least part of the Pareto front. And in the second step we prove that only those designs within our derivation are the Pareto front. So we are not excluding anything. And this can be done by showing that all other designs, so all other designs which are not covered by this, so by the gear ratios and the upper bound of the power of the actuator, are dominated. So all other designs are indeed dominated. So let's start with the first step. So here we want to show that the designs within the bounds are non-dominated. So what we want to do is we are assuming that, so we want to prove in a way that we assume that there is a design A with a different, so with a different gear ratio and a different power exists that differs from our Pareto front definition, but is dominating it. And we can just show, and we want to show that this is not possible. So what we want to show is we want to show that there is a Y1A which is smaller or equal than Y1 of our Pareto front, and also, so we are saying it's dominating our Pareto front, so also Y2 of A is also smaller or equal to Y2 of our definition of the Pareto front. And when we are looking at Y2, we can conclude right away that if that's the case, so if this is indeed true, we know from the formula that, because remember, so this is the formula for the second quantity of interest, that this must also hold. Wait. And from this we know that the gear ratio of the design A must be smaller than the gear ratio of the Pareto front. Sorry, that was a small typo. And so we know that I roof is smaller or equal than our I from the Pareto front. But since we are assuming that our design is different from the one we have at the Pareto front, that means that our power, so of design A, our power of the EPS must be smaller than the upper bound, because the upper bound is part of the Pareto front. And from that, we can, since we know, and we had that on the first slide, that we want to have the maximum amount of power, this cannot dominate the Pareto front design anymore, because if that's the case, then we know that the first quantity, which has, so remember, so the first quantity, let's say Y1 roof, is minus the performance divided by the formula we derived before, so the resistance force and the gear ratio minus the torque at the steering wheel. So this is then bigger than the first quantity of interest of the Pareto front. And and I'll just finish that quickly. And since this will violate our definition, we can tell right away that this cannot be true. So this was step 1. So it's impossible that there exists a design that differs from the Pareto front but dominates the design at the Pareto front. So the first step is done, and we now move on to the second step. Step 2 is now carried out to show that we're not excluding any other designs. So we want to ensure that our definition of the Pareto front, so all gear ratios combined with the upper bound of the power of the actuator, is indeed the Pareto front. So I know that the last slide and also this one is a bit theoretically, because one can conclude that right away from the sketch we made, but still. So step 2 is all our designs are dominated. So we want to prove that for an arbitrary design B with a given gear ratio tilde and P tilde for the power that is different from our definition of the Pareto front, there is also a design C that is dominating design B. So all the other designs that are not part of the Pareto front are dominated, and therefore indeed our definition is correct. So the mathematical proof is pretty straightforward. So what we just need to show is that we want to compare two designs, so B to C, so both have the same gear ratio, and when it comes to the power of the actuator, we know that the power P tilde is always lower than our definition of the Pareto front, because it's not allowed to be part of the Pareto front. Okay, so it's always smaller than the upper bound. And from that we conclude, as I said, we are comparing an arbitrary design. So for this arbitrary design, the second quantity C has the same gear ratio as the design B. So because it only depends on this quantity, it's of course equal, which is not violating the definition of dominating a design. So this is still okay. And for the first one, we know that since we always need to go up to the upper bound of the power of the actuators. Therefore, we know that if we do that for our design C, and this is also part of our Pareto front, and this is the important fact that we know that the design C with the same gear ratio and the power at the upper bound, so this is part of our definition of the Pareto front, is always dominating our arbitrary design point, and is therefore smaller than the design point at B with the same gear ratio but a lower power for the actuator. And by this we have indeed shown that all other designs are dominated. As I mentioned, it's a bit theoretically, but having done that, we can now set up the Pareto front. So here we have the formulas for it. So this is the formula for the first quantity of interest, and this is the formula for the second quantity of interest. And what we do now is we can now insert the one equation into the other to have, like, what was the initial idea, so to calculate the Pareto front by displaying one quantity of interest as a function of the other one. So we're now inserting the equations, and then we end up with the first quantity of interest is equal to the upper bound of the actuator power divided by the resistant force multiplied with the end rod position here, stop here and stop, and also divided by y2. So we are now inserting this from this equation here minus the torque at the steering wheel. So, and having done that, we have now an expression that only depends on the first and the second quantity, because this is now not that's not a design variable anymore. This is the upper bound of our power, and so it only depends on y1 and y2. And what we also have is we have now a limitation of our Pareto front, which is between 6.3 and 9. And on the next slide, we also see a numerical. So here we plotted different designs, and you can also see in MATLAB, and we can also see that the Pareto front is the line we already drew before, and all the other designs here are the dominated designs that are not part of the Pareto front. For the next exercise, we have our known two-bar truss. As a design variable, we have the cross-section of the two bars, and the objective or quantity of interest is the displacement at the tip. And the scenario here is that there are two parties involved. The production planning department wants to reduce the mass to save material costs, whereas the first department, the engineering department, asks for a maximum of stiffness, which is the minimal displacement U. So with this maybe kind of artificial example, we want to show some main ingredients of meta objective functions, and we can start right away with the tasks. The first task is about single objective optimizations. So one time with respect to the stiffness, so the displacement, and the other time with respect to the mass. For that, we can use the formulas given on the right side and also known from the lecture. So when we want to minimize the displacement or maximize the stiffness, we can formulate the following optimization problem. Minimize F1 with the formula on the right side. Design variable is the cross section, and we can enter the values out of the table, and then we will end up with 18.23 millimeters to the power of 3, and the cross section area in the denominator here. We don't have inequality or equality constraints, but we have bounds on the input variables or design variables with a lower bound as well as an upper bound for the cross-sectional area. And this problem can be solved by just looking at it, because we want to minimize the displacements or maximize the stiffness, and that's pretty straightforward. We have to go to the upper bound of the input design space. So the cross-section area is 150 square millimeters, so that's the upper bound, and the displacement can be also calculated with that, which is 0.122 millimeters, as well as the mass with the cross-section area, which is 2.86 kilogram. The same thing can be done for minimizing the material costs, so minimizing the mass. So here we have cost as the term, and then we minimize the second function here. So we minimize F2, and same thing, we can enter the values out of the table, and we end up with 19. We end up with with 19.07 to the power of minus 3 kgs divided by millimeters, square millimeters, and multiplied with our design variable here. Also subject to only upper and lower bounds, so same thing, since the design variables are the same. And here it's also easy to solve, so this time we will go to the lower bound. Of course, we want to reduce the mass here So the result this time is the lower bound with 10 square millimeters. The displacement is of course way higher, so here we have 1.82 millimeters, but the mass is of course, because this was the objective, lower with 0.191 kgs. Afterwards, we now have to set up the linear mid-objective function. So remember in the lecture we had different types of mid-objective functions. Here we want to have the linear one, which is straightforward, just it's phi, the first quantity of interest, which is the system stiffness or displacement, and here we choose the weighting factor with respect to the mass, and we can afterwards enter the values we calculated earlier. And with that, we set up the mid-objective function. One important fact is that also the weighting factor has units, because otherwise the first and the second quantity of interest doesn't fit together unit-wise. So this is the one thing we also need to consider later on. So the next slide is about how to choose or how to set up the weighting factors, and this is a crucial part for multi-objective optimization, because choosing a right or reasonable weighting factor is not the easiest task, and sometimes you just have to guess, but otherwise you have some information. And here the scenario is that an estimation shows that an improvement in displacement of 1 millimeter is has the same worth as a loss of weight of 500 grams here. And the figure here illustrates that. So we see the weight on the y-axis and the displacement on the x-axis. And out of that we can calculate now the weighting factor. And the only important thing is that you choose the values. So since it's a linear mid-objective function, this works. And it's independent of the point where this measurement was taken. And the only important thing is that you have the numerator and denominator for the right values. So since the weighting factor was chosen with respect to the mass, it's calculated with 1 millimeter divided by 0.5 kg. So we have 2 millimeters divided by the kgs, and afterwards we are also supposed to calculate the optimal cross-section. So what we need to do is now we need to take the derivative of our mid-objective function with respect to our design variable, and this is supposed to be equal to 0. And if we do that, we end up with minus 18.23 millimeters to the power of 3, and since the cross-section area is in the denominator, we have the minus sign in the front, and this is to the power of 2, and this plus 19.07 to the power of minus 3 kg divided by square millimeters, and the whole thing, because it's linear, is just multiplied with the optimal weighting factor. And if you do that, you end up with an optimal cross-section area of 21.9 square millimeters for this specific weighting factor. Afterwards, the task is about varying this weighting factor. So it's about seeing what changes if we change the weighting factor, which is sometimes, as I mentioned, not so easy to choose. And here you already know some results in the table. So the first one, with a weighting factor of 0, is the equivalent. So the weighting factor was chosen with respect to mass, so the mass is cancelled out. So we are just maximizing the stiffness, so we are at the upper bound of the cross-section area. Whereas the other way around, if the weighting factor is infinite, then we are just going for the mass here, and you see that we are at the lower bound. On all the other values are within between. And there you get a first idea on how the Pareto front looks like for this design example. We are using this plot for the next exercise too. Lastly, we draw the contour lines of the linear mid-objective function with the calculated weight. And we also are supposed to sketch a possible Pareto frontier with the data generated in the exercise before. So the first thing we need to do is we can again write down our meta objective function, which is just the displacement u plus our calculated weighting factor multiplied with the mass. We can also enter the calculated value here. So it's 2 millimeters divided by kg multiplied with the mass. And to make it easier, we can put the mass on the left side. So we end up with the following formula. And with this, we can then draw the contour lines, because for a chosen phi, we can do one line of the linear meta objective function. So we can just vary the phi now with a given weight, and this is how the meta objective function can be constructed. So maybe just as an example, I try to do it. So the slope is 0.5. It goes down, so it should end up here. And then now wait, we are here roughly. Okay, it should look like that almost. And exemplary, I can do some more contour lines, and this is how you can draw them. And one specific characteristic of the contour lines for a given weight is that the optimum based on the weight is always tangential to the Pareto front. So let's say for this weight, at this point, the slope is equivalent to the sketched contour lines I have here. So I can also try to connect those points for the Pareto front here. So we are now here, and then this to that. And so at this point, the slope is tangential to our meta objective function. The next exercise is a pure computer exercise concerned with a 10-bar truss. Here our engineering problem is to optimize the 10-bar truss with respect to the cross-section areas. We have two quantities of interest, which are the tip displacement and the mass, and a third quantity of interest, which is concerned with the material strength. And for this we have now 3 different exercises, and we can start right away with the first one. Before we start with the actual exercise, I want to introduce the optimization problem. So now in the official mathematical form, so we have our meta objective function phi, which is optimized with respect to the cross-section area. So these are the design variables. And on top we have a weight, which is not affected by the optimization itself, but can change the meta objective function. And on top we have a nonlinear constraint here for the material strength, and we have lower and upper bounds for the design variables. And also on Moodle there were a lot of different files which I also want to explain, because it might be a bit confusing in the first place. So how do the different MATLAB scripts and functions fit to the given optimization problem? So first of all, how to start the optimization problem is with our script file truss_opt, and this script file initializes the optimization problem, and afterwards we have different functions. The first one is the multi-objective function. So this one is the file we will also edit within this task, and the multi-objective function then accesses 2 different quantities of interest or objective function with a single objective, so with respect to mass and displacement. For displacement, we need another function, which is the system response. So here we have truss FE, so the finite element model for the 10-bar truss. On top, we have our nonlinear constraint function for the material strength, and this one also needs the truss FE function, and that's the reason why this is in a separate file, that both functions here can access the system response. And the last file is the truss_out function. So this is the same as in the exercise 6.3 in the last exercise. So we also implemented something to visualize our optimization procedure. Having explained that, we can now proceed with the with the task itself. So here we are supposed to implement different objective meta functions, a linear one, a quadratic one, and a worst case function. And here you can just open the multi-objective function and enter the respective equations, which were also taught in the lecture. Afterwards, we are supposed to optimize the truss with a linear objective function and weight of 1000. And you can just then open the truss opt script, so the script we use to start the optimization, and you can, after having edited the multi-objective function, you can now type in linear and the respective weight, and then you just start the script. And after a few iterations, you will end up with the following 10-bar truss. Here we also see the deformed state of the problem. And on the right side, we also have the results. Maybe one word to the results. So depending on the version of MATLAB you're using, there might be some small differences in the mass and the displacement. So this is only with respect to some numerical errors. So as long as it is in the same range, you did everything right. Afterwards, we now change the optimization type in the multi-objective function from linear to quadratic, and we also introduce a loop in the truss opt file, and then we just iterate, because what we want to do here is we want to plot some points of the Pareto front here. So we want to vary the weight. So remember, for each weight for a meta-objective function with different objectives, we get a different optimal result. So by varying the weight, we get for each weight a point on the Pareto front. And here we want to vary it from 1000 to 100,000 in 5 steps. And because of that, we can set up this loop, for instance, from -2 to 2 with this formula for the steps of the weight. And then for each step, we carry out a single optimization. And if we do that, we can end up with points like that. So this is an exemplary Pareto front. One important thing is that since we need to carry out an optimization per point, this is really time consuming. So for such a small problem, this can be done quickly, but for larger problems, you can imagine that this is not always possible. Instead of setting up a meta-objective function phi, we can also use genetic algorithms that we introduced in lecture 6 to this task. So what is done here is that we just give both objective functions, and here also, of course, so in the MATLAB code, we just give both objective functions as a handle, and on top we also give our constraint function here. And conceptually, how it works is that in the first iteration, the genetic algorithm just creates different individuums, like we also taught in the lecture, and afterwards they are evaluated. And they are evaluated, so the fitness function is based on two concepts. So the first one is just that we are looking for non-dominated solutions, like we also had in the first exercise of today. And the second objective is a distance measure, and the distance measure is used to distribute the designs along the Pareto front. So these are the two objectives that are tried to be optimized by the genetic algorithm here. And now we should use so the structure of the files is the same as for the last exercise. The only difference is we don't need to set up this multi-objective function, but we just give the two objective functions instead. And here we run the truss Pareto script, and the results are depicted here. So we see that there are a lot of designs along the computed Pareto front. So remember, this is the Pareto front based on single gradient-based optimizations. But we also see one problem, so the genetic algorithm is not capable of giving us designs along the whole Pareto front, but only in a certain range. And this is just due to, the genetic algorithm is an heuristic algorithm, and then if a result is not satisfactory, then you need to change some settings. And here we also saw the settings were only a population size of 100 and 4 generations. Of course, this was done because of computational reasons. So to get better results, one can increase these parameters or also other parameters to get designs along the whole Pareto front here. Lastly, we have another problem of the automotive industry. So here we are supposed to find the optimum of a chassis spring stiffness and anti-roll stiffness while satisfying, and now it's not a X is better design but requirement based. So we have requirements on the eigenfrequency of the vertical vibration and also a requirement on the roll angle for the lateral acceleration. So in general, we see here the suspension of a car with two main elements. So we have the anti-roll bar and we have the chassis spring. On the next slide, we have also a mechanical model to illustrate the working principles of the suspension. So here you see that we have a rotational stiffness of the anti-roll bar. So this is against a rotational movement of the car. And then we have the springs that are connected to the wheels that give a stiffness with respect to the translational movement of the suspension. We have some values given as the front axle load. So this is half the load of the car. We have the track width B. And we have also the height of the center of gravity as well as a lateral acceleration of the car body. We have two quantities of interest in this problem. So the first one is the eigenfrequency of the vertical vibration, and the second one is the roll angle at a given lateral acceleration. For that we need two system equations. The first one is rather simple. So here, because we have two springs in parallel, we can just take the stiffness times 2 and divide it by the system mass, so half of the car body, and the root of it is the eigenfrequency. And okay, I also like the animation, but there is a deeper purpose as well. So here we have the system equation for the roll angle at the lateral acceleration. But once again, I must stress that actually there are two perspectives. So for this lecture, you don't need to derive equations like that. So this is an equation out of the driving dynamics field, which you can derive by having all the stiffnesses, the lateral acceleration, and certain geometrical values, and then you can end up with this expression for the angle. But for this lecture, you don't need to derive such equations. We will give them to you if needed. But on the other hand, so in real applications of optimizations, it's always really important that you have knowledge in both fields, because both fields, in a sense, you need to have knowledge in the specific field where you want to carry out the optimization, because you need to understand the background of your problem, and you also need to make sure that the results that you produce with the optimization make sense. So you need to have knowledge in this field. So for this task, you need to have knowledge in driving dynamics, and second thing is you also need to understand the optimization background. So you need to understand if the optimization was from a mathematical point of view successful and so on. So that's why, so in this lecture, you don't need to have the backgrounds, but if you want to apply the knowledge of this lecture to specific problems, make sure that you also understand the problem you want to solve. And our first exercise is now set up the standard form of the given optimization problem and combine the two objective functions into, and that's also one task, into an appropriate objective meta function. So first of all, we need to write down all the ingredients needed for this. And I need to activate my pen first. So we start with the design variables. So we have two design variables that are one time the stiffness of the springs and the stiffness of the anti-roll bar. What else? We have two objective functions here. So the first one with respect to the springs, which is the eigenfrequency calculated by the system equations we gave you. So 2 times the stiffness of the spring divided by the mass, and then the root of it. And secondly, we have the lateral acceleration, which is based on both stiffnesses. So here both stiffnesses, and then we can again just use the formula of the page before. So this is equivalent to this equation. And you can also add up both stiffnesses here. Having done that, we have design targets, so we have requirements on both quantities of interest. So the first one, F1, is supposed to be, so we have two-sided requirements, it's supposed to be between those two values, whereas the lateral acceleration is also, there are also two-sided requirements on this quantity of interest. And the second one is this. And lastly, we have the design space. So these are the bounds on the design variables itself. So we have also a lower bound for the spring stiffnesses of the translational movement. And sorry, I forget the units. So this is of course stiffness, and here also. And we have also bounds on the anti-roll bar, as well a lower and an upper bound. The lower bound is just 0, and the upper bound is 50,000 Newton per meter. Lastly, we need to choose an appropriate meta-objective function, and there are different choices for that. So we are dealing with requirements, so we are not dealing for a design problem with X is better, but for requirements. So we are here, and we also have two-sided requirements. So therefore we know in which row we should choose from. And here it's even easier because linear meta-objective functions for two-sided requirements especially, they are not suited for our problem because they do not distinguish between good and bad designs. So they can, because of the linear formulation, you could have one requirement not satisfied, but still it's a better solution. And the second one is that especially here they cancel each other out. So because of the linear nature, you just end up with a constant term, and the quantity of interest itself is cancelled out. So the linear meta-objective function is not appropriate. And I mean, this is out of the lecture, so Professor Zimmermann also explained it to you. And also for quadratic objective meta functions, it's kind of similar. So here we also have two problems. So first one is again with the differentiation between good and bad designs, and second one here even because of the quadratic nature, designs that differ from the given area might be penalized even. So if they differ from the upper or lower bound, they might be penalized by the formulation, so this is also not a proper formulation. So we end up with having only one choice, which is the worst case objective function here. And now since we have the standard form of the given problem and we have the objective functions and also choose an appropriate formulation, we can now finish this task by writing down everything that is needed. So first of all, we write down our meta objective function, which is the worst case function. So we have the maximum operator, so we are only optimizing for each iteration on the worst quantity of interest with respect to the requirement. Here we have two-sided ones, so we have 4 terms. So we have the eigenfrequency with respect to the lower bound, and we normalize, or we do the weighting with respect to the upper and lower bounds that are given. So here it's this one, it's upper bound minus the lower bound, and we do the same with respect to the upper bound here. So then the entries are changed, so it's as the following, but the weighting is carried out the same way, so it's different between the upper and the lower bound. And we do the same with respect to the angle and the lateral acceleration, or at the point of the lateral acceleration. So once again, two-sided, so it's the same as before. And again, normalized with respect to the upper and lower bounds. And also the same for the upper bound, where the order is switched. And this is the meta objective function, and we can also formulate the optimization problem. So what we want to do is we want to minimize the meta objective function with respect to our upper and lower bounds. So once again, we had that before, so we can just write it down again. So with the upper and lower bounds for the chassis springs, and also we have the upper and lower bounds for the anti-roll bar, and the upper bound is 50,000 Newton per meter. And if you solve that, then you end up with the following values that are and for the anti-roll bar stiffness, so to solve that, we carried out an optimization in MATLAB. So this was not part of the exercise, but still we can give you the values of that, and also maybe the values of the quantities of interest here, or of the both objective functions. So for the eigenfrequency, we end up with the following. And for the angle, it's 3 degrees. And we can also have a look on how the contour plots look like. So here we have the contour plots for the given problem, and also with our final design in the middle of the contour plots.